Hi everyone. Welcome back to Dave's Math channel. I'm your host David Tare, and this is my second video in my sub-series on numerical integration. Today I'm going to talk about another rule for a numerical approximation of a definite integral. The rule is known as the midpoint rule, and I think as you can see from this slide, the idea is you take, here they just show four subintervals of the integration range. And what they're doing is, in each of these subintervals, they're taking the midpoint as the approximate value of f of x on that interval. So that's kind of how it works. But anyway, let's begin. So here's what it says in more detail. So the midpoint rule is just a rule for where you're trying to estimate the value of a definite integral. I equals the integral from a to b of some function, some well-behaved function f of x. And the way we do that is, remember, this is an example of a Riemann sum. And in general, Riemann sum is just a sum where you're sampling values of the function on each subinterval. In this case specifically, you're sampling the values at the midpoint. So in this case, our x sub k are just the midpoints, which we call m sub k. And we can come up with a formula for those. M sub k is just x sub k plus x sub k plus 1 all over 2. It's just the average of, or if you like, the mean of xk and xk plus 1, where our xk is just the point. We've divided our interval into capital N subintervals, and it's just the anyway, m sub k is the formula for the midpoint. I think it's pretty easy to see that. And we can come up with a specific formula for that, which I do on the bottom of the slide. It's just a plus k plus 1/2 times delta x, where delta x is b minus a over capital N. So that's how you do that. That sounds like a lot, but you'll see it's not that hard if you do some examples. So anyway, and then, just to be a little more specific here, well, yeah, that's just basically saying what I already said. So I kind of jumped the gun when I was talking. But anyway, that's the midpoint rule, and this is how we use it. So let's do a couple examples. And I think the easiest example, this is the same example. I'm giving the same two examples I gave in my last lesson. We're going to integrate, first we're going to integrate the function f of x equals x from 0 to 1. That just gives you a right triangle with legs of length 1, and we all know the area of this right triangle is 1/2, so I should be 1/2. Well, let's see what the midpoint rule gives us. So now we're going to use 10 subintervals, so capital N is 10. So now we just apply the formula. Let's just do one step at a time. So m is given by the sum k going from 1 to 10 of f of m sub k times delta x. We know delta x is 0.1. It's just 1/10 of the width of the whole integration range. So we can actually pull that outside if we want. But then let's just simplify the integrand. F sub m sub x. Remember, f of x is x, so f of m sub x, m sub k is just m sub k. So we just plug everything into this formula, and when you work out the details, you're gonna get this simplifies to 0.005 times the sum k going from 0 to 9 of 2k plus 1. You might know this. If you're summing all the odd numbers up to some range, say 9 in this case, that's just going to give you the square of the last summand plus 1. So in this case, it's going to be 10 squared or 100. So you're going to get 0.005 times 100, which is just 0.5. And that's nice because look, the midpoint rule gave us the right answer in this case. Which isn't really that much of a surprise if you think about it. I mean, this function is so simple, f of x equals x. It's a linear function, so it's not a surprise that if you take the midpoints, you're going to get the right answer, because the midpoints of a line kind of give you the average value of the line, the function along that range. So anyway, it works exactly for the case of a line. I think that's always true. If you're using the midpoint rule on a linear function, it's always going to give you the exact answer. That's a useful thing to know. but in general it doesn't. And here's an example where it doesn't give you exactly the right answer, but as we'll see, it gives you something very, very close. So now this is the second example I did last time. So let's do it again. Now we're trying to estimate the value of the integral of x squared going from 0 to 1. And as I mentioned a few times already, the value of I is equal to 1/3 in this case. This is the area under parabola. And I did it analytically a couple videos ago when I showed you the exact answers of 1/3. Of course, I was jumping the gun there. We still haven't proven the fundamental theorem of calculus, which is how we did that. But let's use the midpoint rule to see what we get here. And you can apply the formula again. And this time I think I'll spare you the details. You can work them out yourself if you want. But when you're done, the answer you get, which I was kind of surprised when I did this. I actually did this problem for the first time myself when I made this video. You get 0.3325, which is very, very close to 1/3. It's only off by about 1/4%. Pretty remarkable. This wasn't a difficult calculation. I mean, we just used 10 subintervals. Maybe it's a lot of, it's a lot of grinding out, but nowadays people use computers quite a bit, or even a fancy calculator. It shouldn't be too much work to do this. It's not that kind of much work. You probably do this calculation in about 5 or 10 minutes. So in just a few minutes, you can use the midpoint rule with this function x squared and get an answer that's only off by about 1/4%, which I think is pretty nice. So anyway, that completes my video for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.